Greetings, Earthmen. I wanted to do a little video this morning about my favorite topic, which is coils. I'm going to go pretty fast through this. Here's a drawing of a coil, the end view of a coil. Here's the core. Here's a rotor magnet approaching, and it's going to go on by the core as the rotor goes around. There is a magnetic field around this magnet. And when it interacts with the core, it starts to fill it up with flux. Iron has one rate at which it fills up. Met glass has another rate. Ferrite has another rate. Other core materials have different rates at which they'll fill up with flux. Well, what has to happen what has to happen here is this magnet approaches the iron core. It begins to fill up with flux. There's a tipping point before which not really anything happens here, but at a certain moment in time, there's enough flux in here to start the creation of electricity in the coil. Now, the coil, voltage and amperage don't travel at the same rate, and it takes time for this coil to fill up, especially when it's under load. And then it creates, when it's filled, it creates an electromagnet in this iron core that repels the approaching magnet. Okay, well, there's a timeline here, okay? There's some things that have to happen on this timeline. The first thing that has to happen is this magnetic field has to come within the range of the iron core, and it starts the reaction. The second thing that has to happen is this tipping point has to be reached where it begins to generate electricity in the wires. The third thing that has to happen is that this has to be turned into an electromagnet to repel the approaching magnet on the rotor. Now, from my experiments, any coil can be made to accelerate under load, because all you have to do is speed this rotor up enough that between the time the magnetic fields interact and this turns into an electromagnet, this magnet has moved to here. That's all you have to do. That's just a matter of speed. If this field begins to interact and turn this into an electromagnet, and this is there, then when it turns into an electromagnet, it pushes it away. Now, this is not going to fill up with flux any faster once it begins to interact with the magnetic field, because iron can only fill with flux at a certain rate of speed. Ferrite is different, met glass is different. So it's only going to fill with flux at a certain rate of speed. So accelerating the rotor just puts this magnet in an alignment with this at a faster moment in time. So any coil, and I've wound many coils, you can get any coil to speed up under load if you speed up the rotor. Now, what we have done is we have, because of the way we wind the coils, we have increased the capacity of this coil to accept the electricity that's storing up in there, which has to store up to a certain point before it turns this into an electromagnet. So all we have done by the way that we wind the coils is slow down the three-step process long enough to help this get to here without having to change the speed of the rotor. But you can either increase the speed of the rotor, or you can wind coils with greater capacitance, or you can do a combination of both, and you still get the effect that you need, which is this magnet is right here when this turns into an electromagnet and it repels it away. That is the basis for everything that we're talking about. Now, I've learned that you don't want it to be right there. You don't get the greatest output of the coil when that happens. You want a kind of a neutralizing effect, and so you adjust the RPM of the rotor, or you adjust the length of the wires in your coil, or there's a lot of things you can adjust to make it happen when you want it to happen, and that's the effect that we're trying to control with what we're doing.